Section 5.11 Running Key. Running key is similar to auto key, but instead of a short keyword or key phrase, running key uses a key text that may be as long as the message itself. Running key has never been widely used in practice because it requires both parties to get the key text exactly letter perfect. If one party remembers or copies the key as "Mine eyes have seen the glory of the coming of the Lord," but the other party remembers the key as "My eyes have seen the glory of the coming of the Lord," then they will be unable to communicate. One way to deal with this problem is to use a key text from a printed book that both parties have, although they must carry the book with them. This is not a problem for computer communication, because a computer can store thousands of books. Again, assuming the Balasso tableau with the standard English alphabet, running key is straightforward, albeit laborious, to decrypt. One technique, which works for both auto key and running key, is to guess a likely word that may appear in the text. The word could occur in either the key text or the plain text. The cryptographer will need to untangle this later. The probable word, or crib, could be a common English word like the or and, or it might be a word related to the suspected subject matter. For example, if the message pertains to trade negotiations, then likely words might be tariff, shipping, representative, bargaining, and similar. The idea is to try the probable word in all possible positions in the message. This is called word dragging. Knowing the plain text word and the corresponding ciphertext gives you a snippet of the key. If the word is correctly placed, then this fragment will look like normal English. The longer the probable word, the more confident you can be that it is correct. Once you have found a word, you try to guess the letters, then the words that precede or follow it in the text to widen the breach. There is a second technique, one which is suitable for computer solution. This requires a new mathematical concept called conditional probability. This is the probability that an event A will occur if event B also occurs. The probability of a single event A is denoted P brackets A, and the conditional probability of the event A given the event B is denoted P brackets A vertical line B. If AB denotes the event A and B, then the conditional probability of A given B is P of A given B equals P of A and B over P of B. That means P of A and B equals P of A given B times P of B. An example may help to clarify this. If you are throwing two standard dice, the probability of throwing a 12 is 1 over 36. However, if you throw the first die and the result is 6, then the chance of throwing 12 becomes 1 over 6. Let A mean throwing 12 and B mean the first throw is 6. Then P of A equals 1/36 and P of B equals 1/6. P of A and B means throwing a 12 with the first throw being 6. P of A and B is also 1/36, because if you throw a 12, the first throw has to be 6. Using the notation for conditional probability, P of A given B equals P of A and B over P of B equals 1/36 over 1/6 equals 1/6. So the conditional probability of throwing 12 when the first throw is 6 is 1 over 6. Let's use conditional probability to solve a running key cipher. The tools that are needed are tables of single-letter bigram and trigram probabilities. These can be compiled by counting the letters, bigrams and trigrams in a large body of text. You can find many such bodies at the Project Gutenberg website. www.gutenberg.org. Select the plain text option. You can also find some tabulations on the internet. You will need to assign a probability for every possible bigram and trigram, not just those found in that body. For bigrams, this is obvious. If AB is a bigram that did not appear in the count, you could set P of A and B equals P of A times P of B. However, I suggest setting it lower simply because AB was never found. I use P of A and B equals P of A times P of B over 3. Once you have a complete set of bigram probabilities, you can extend this to trigrams by setting P of A, B and C to the greater of P of A times P of B and C and P of A and B times P of C. Again, I suggest setting them lower because the trigram ABC never appeared. For example, set P of A, B and C to the greater of P of A times P of B and C over 3 and P of A and B times P of C over 3. These artificial probabilities mean that the total probabilities for all bigrams and all trigrams are greater than 1. Mathematically, this is nonsense, but it has no practical effect. Now that we have the necessary tools, we can tackle a running key cipher. Choose a starting position in the message, say S, and try all possible key trigrams in positions S, S+1, S+2. See what the corresponding plain text trigrams are. Multiply the probabilities of the key trigram and the text trigram to get the probability for that placement. Keep the top 10,000 of these placements and discard the rest. For each of the chosen trigrams, try all possible key letters in position S+3 and see what the corresponding plain text letter is. Suppose the key trigram is JKL, the next key letter is M, and the corresponding plain text tetragram is ABCD. You can estimate the probability of the key tetragram JKLM by using the conditional probability P of K, L and M given K and L, which is the probability that an M will follow the bigram KL. This is calculated from the trigram probabilities as P of K, L and M over P of K and L, which is the probability of the trigram KLM divided by the probability of the bigram KL. The probability of the tetragram is thus estimated as P of J, K and L times P of K, L and M given K and L. This is done for both the key tetragram and the plain text tetragram ABCD. Estimate the probability of this placement by multiplying the probabilities of the key tetragram and the plain text tetragram. Again, keep the top 10,000 and toss out the rest. Keep going until the solution becomes obvious. This can all be done by computer without any human supervision. Fictionnaire running key using standard alphabets is rated 4.